Trey Foster. I'm a graduate student at Mississippi State University under the direction of Dr. Dan Reynolds, and the title of this presentation is The Comparison of Off-Target Movement of Various Size Spray Droplets when applied with an open boom versus a red ball hooded boom. With the development of soybeans and cotton resistant to 2,4-D or dicamba comes an increase in the use of these auxins for weed control. Auxin herbicides are growth regulators that are generally used for controlling broadleaf weeds in grass crops and pastures. These herbicides have been around for many years, and there are very few weeds that have developed resistance to them. So we expect there to be a significant increase in the use of these new auxin-resistant crop systems. The problem lies with farmers that choose not to use the new auxin-resistant crop systems or that have sensitive crops on their farm or adjoining farms. 2,4-D and dicamba have a history of drift problems, partially because very low doses can cause severe injury to sensitive non-target plants. For precautionary reasons, the first labels for the use of 2,4-D and dicamba on the herbicide-tolerant crops will not allow aerial application. This will decrease the potential of a drift event occurring, but will not be an absolute solution to the problem. So what is particle drift? Particle drift is the movement of spray particles and vapors off target, causing less effective control and possible injury to susceptible vegetation, wildlife, and people. That definition is adapted from the National Coalition on Drift Minimization in 1997. There are four major factors influencing particle drift: wind speed, boom height, spray particle size, and distance from susceptible vegetation. And the main factor that we're going to be looking at for this project is spray particle size incorporated with application technology. Main concern when talking about spray particle size is coverage. Past research suggests that smaller droplet sizes provide increased control over larger droplet sizes, especially for contact herbicides, because the larger droplets tend to bounce off of the leaf and droplet retention is decreased. So just to break down this chart for you, you've got the droplet category on the far left, ranging from extremely fine to ultra coarse, and the corresponding symbol that goes with the droplet category, as well as the color code that corresponds with the droplet size. And at the far right, you've got the approximate volumetric mean diameter range, with extremely fine being less than 60 and ultra coarse being greater than 650. So to set this chart up, you've got droplet size in microns on the y-axis, you've got cumulative volume fraction on the x-axis. On the right, you can see spray droplet sizes ranging from extra fine down to ultra coarse. And what this graph is a spray nozzle classification by droplet spectra. If you look at extra fine, you can see that throughout that cumulative volume fraction, there's not much variation within size of droplets for that spray. Most of those spray droplets are going to be within 0 to 100 microns in size, so not much variation. Likewise, if you look at the other extreme with the ultra coarse droplets, you can see that half of that spray is going to be 650 microns or greater, as we stated previously in the presentation. But with those ultra coarse droplets, you're going to still have droplets that range just above 300 to 650. So basically what this graph is showing you is that even though you increase the size of spray droplets, you're still going to have smaller droplets within that spray as you increase in the size of the spray droplets. What this area in red is showing is the amount of highly driftable particles. It's what's considered to be highly driftable particles, and you can see that extra fine, very fine, fine, and medium droplets are all in that red zone that is considered to be highly driftable particles. So the proper combination of droplet size and spray equipment will be needed to reduce the potential for drift. So we conducted this experiment at North Platte, Nebraska. We used a formulation with Roundup Power Max at 32 fluid ounces per acre and a PTSA dye at 5 grams per gallon. And that PTSA dye was our marker for the amount of drift that we had. All treatments were sprayed at a GPA of 15. So just to break this chart down for you, we've got treatments on the far left. We used two different boom types, open boom and a red ball hooded boom, and we used various nozzle types, pressures, and speeds. And the main thing I want to point out is on the far right is the droplet sizes. So we produce 4 droplet sizes: ultra coarse, very coarse, medium, and fine. And we used each of those 4 droplet sizes with each boom type. And you can see on the left our red ball hooded boom sprayer, and on the right our regular open boom sprayer. So for the field layout, we had one 600-foot pass down the field for each treatment. We placed small mylar cards in 3 lines ranging from 13 feet all the way down to 210 feet. downwind of the treated area. We also place large mylar cards at 246, 295, and 344 feet downwind of the treated area. We placed 3 petri dishes within each swath. Small mylar cards were placed upwind of the treated area as the untreated check, and we recorded the wind using a Kestrel wind meter for each of the wind speeds for each treatment. This is just kind of a picture showing you how we set up the field, so you can see the spray direction in the treated area going across the top. You can see our 3 rows of mylar cards in blue. You can see the wind running perpendicular to the treated area, and you can see our upwind check that is away from the wind in the treated area. So on to data collection. Petri dishes and mylar cards were collected at a minimum of 2 minutes after the sprayer stopped. We recorded start time, stop time, wind speed, and wind direction, and mylar cards and petri dishes were analyzed using a fluorometer. So for analyzing the samples, we used distilled water and isopropyl alcohol, and for the petri dishes and the large mylar cards, we used 1.35 fluid ounces of that solution for each sample, and for the small mylar cards, we used 0.68 fluid ounces of solution for each sample. The values that we received from the fluorometers were in relative fluorescence units, or RFU, and what that relative fluorescence unit is a measure of how much light is reverted back to the sensor element of the fluorometer. So the higher the RFU value is, the more drift we saw. On to the results. To set up the charts, and all of the charts will be the same throughout the rest of the presentation. We have the RFU, the relative fluorescence unit, on the y-axis, and distance in feet on the x-axis. So for the fine droplets with the open boom, at the first distance we had a RFU of over 3,500, and tapering down as distance increased. Now here is the same fine droplets with the incorporation of a red ball hooded boom. You can see that at that first distance we had less than 500 RFUs, and then tapering all the way down until it disappears after 148 feet out. So with the use of the medium droplets using the open boom sprayer, at the first distance we had an RFU of just shy of 2,500, and tapering down as distance increased until about 210 feet. And here is the use of the red ball hooded boom. At that first distance you can see an RFU value of about 250, and then decreasing steadily until about 246 feet out. And with the use of very coarse droplets using the open boom, we had that first distance RFU value of around 750, and decreasing all the way down to about 210 feet out. And with the red ball hooded boom, the first value RFU value being around 25 to 50, and then constantly remaining at a very low RFU value throughout the distances. And finally, with the ultra coarse, which is the largest droplet that we used, here is the open boom. We see it's just under 500, probably around 300 RFU, and then tapering down until it almost disappears at 148 feet. And here is the hooded, red ball hooded boom that we used, and it is almost not even able to be seen on this graph, so it's still significantly less than that open boom that we used. So this is the same setup as our previous graphs that we've looked at, and what this is just the effect of droplet sizes on off-target deposition using the open boom. You can see with the fine droplets we had a lot of drift with very high RFU values all the way out to 210 feet. When we switched to a larger droplet size, a medium droplet size, we had a decrease in the amount of drift that we had, but still a very significant amount of drift out to 210 feet. And as we increase the droplet size to very coarse, we have another decrease in the amount of drift that we saw. And finally, with the largest droplet size that we used, which was ultra coarse, this showed us the least amount of drift within the open boom. So in conclusion, for all droplet sizes, the use of a shielded sprayer decreases the amount of a particle drift found on the mylar cards. As the droplet size increases, the difference between the hooded spray boom and the open spray boom decrease, especially with the very coarse and the ultra coarse droplet sizes. The use of a hooded sprayer will allow an applicator to achieve maximum coverage while minimizing the amount of particle drift that occurs. And this will be important when the applicator wants to use their sprayer interchangeably between herbicide, fungicide, and/or insecticide applications. So for future research, we plan to replicate this study in the next growing season, 2016, to confirm the results that we gathered. This study will be conducted at 2 locations, Brooksville, Mississippi, and again at North Platte, Nebraska. With that, I would like to thank Mississippi State University, Dr. Dan Reynolds, Dr. Greg Kruger, the research associates here, Bo Varner and Graham Oakley, all of the workers and graduate students at West Central Research and Extension Center, as well as my fellow graduate students, and the Mississippi Soybean Promotion Board for their support.